You won't believe how Chinese genius engineers built the tallest highway in the world. The Yaxi Expressway defies every rule of physics and common sense. It climbs over 13,000 feet, through mountains that swallow roads whole, crosses valleys so deep you can't see the bottom, and somehow stays standing in one of the most earthquake-prone regions on Earth. This isn't just another highway story. What these engineers pulled off in 5 years will make you question everything you thought was possible about building roads through impossible terrain. Here's where it gets insane. Picture a valley so deep that when you stand at the edge, the river below looks like a thin silver thread. The Ganjigou Valley plunges 1,800 feet straight down, with walls of crumbling rock that shed boulders the size of cars. Engineers stared at this chasm and realized they had to build a bridge across it. Not a small bridge, a monster spanning 4,232 feet from one side to the other. This single bridge would become the crown jewel of the entire Yaxi Expressway, the tallest structure on a highway already breaking records. But here's where everything almost fell apart. The canyon walls weren't solid rock. They were fractured, unstable formations that crumbled when drilling crews tried to anchor foundations. Every test hole they drilled hit layers of shattered stone that couldn't support the weight of a bridge tower. Wind screamed through the gorge, at speeds that ripped equipment from workers' hands and sent tools tumbling into the abyss below. The construction team needed to install massive cables across this gap, working at heights where one mistake meant certain death. Workers strapped into harnesses dangled over the void, their hands shaking as they connected deck sections 1,200 feet above the river. The solution they came up with is genius. Engineers designed 2 towers reaching 656 feet into the sky, taller than a 60-story building. They didn't stop drilling until they hit solid bedrock 200 feet below the surface, anchoring the foundation so deep that the fractured rock above couldn't matter. The bridge uses a cable-stayed design, with dozens of steel cables fanning out from each tower to support the deck. Those cables now hold up a roadway suspended 1,214 feet above the Ganjigou River, making it one of the highest bridges ever constructed. 4 lanes of traffic cruise across empty air, completely oblivious to the engineering miracle keeping them from plummeting into the gorge. But this was just the beginning of the nightmare. The Ganjigou Bridge was just one single bridge in a highway that would need 270 of them. You heard that right. 270 separate bridges, each one requiring its own foundation, its own design, its own solution to impossible geology. When engineers laid out the route from Ya'an to Xichang, they realized that nearly half of the 149-mile expressway would be elevated structures. 72 miles of bridges. The highway wasn't being built through the mountains. It was being built above them. Here's where it gets insane. Every single one of those 270 bridges sits in an earthquake zone. The same fault lines that triggered the devastating 2008 Sichuan earthquake run directly under the Yaxi Expressway route. Engineers couldn't just build standard bridges and hope for the best. They needed to construct 270 individual structures that could survive the ground, violently shaking, shifting, and rolling beneath them. Coordinating materials for simultaneous construction across dozens of remote mountain work sites turned into a logistics nightmare. Quality control teams had to verify that every bridge, from the smallest 100-foot span to massive valley crossings, met earthquake-resistant standards. One failure anywhere along the route would shut down the entire expressway. What happened next shocked the entire engineering world. The construction teams developed modular techniques that let them build multiple bridges at once, factory-producing components that could be assembled on-site. But the real breakthrough was the seismic isolation bearings installed on every single bridge. These aren't regular supports. They're sophisticated devices that let the bridge deck slide and flex independently from its foundation during an earthquake. When the ground moves, the bearings absorb the motion instead of transferring destructive forces into the structure. The Yaxi Expressway became more bridge than road, a 72-mile chain of elevated structures that could dance with earthquakes instead of fighting them. Then came the most devastating challenge of all. Going over the mountains wasn't always an option. Some peaks were too massive, too unstable, too dangerous to bridge across. Engineers had no choice but to go straight through them. 25 tunnels would need to be bored through solid rock, totaling 25 miles of mountain excavation. The Erlangshan Tunnel alone stretches 8 miles through the heart of a mountain that had defeated every previous attempt to cross it. 8 miles of driving through darkness, through rock that hadn't seen daylight in millions of years. This wasn't just drilling holes through stable granite. These mountains sat on active fault lines, riddled with underground rivers and packed with pressure that could explode without warning. But that's not even the crazy part. The tunnel boring machines hit underground rivers almost immediately. Water didn't just seep into the excavation sites, it flooded them. Thousands of gallons per minute poured through cracks in the rock face, turning work zones into underground lakes. Workers scrambled to pump water out faster than it rushed in, fighting a battle they were losing. Then the rock bursts started. Pressure built up over millions of years suddenly released when drilling broke through, sending chunks of stone exploding off the tunnel walls like shrapnel. Ventilation systems in the longest tunnels couldn't keep up, leaving workers gasping for air miles inside the mountain. Equipment overheated in the confined spaces. Progress slowed to feet per day instead of the hundreds of feet engineers had planned for. The breakthrough came from machines that seemed impossible to build. Advanced tunnel boring machines, equipped with integrated water management systems that could pump, drain, and redirect underground rivers while simultaneously cutting through rock. The tunnel walls got reinforced concrete linings thick enough to withstand mountains literally shifting during earthquakes. Climate control systems were built directly into the 8-mile Erlangshan Tunnel, constantly circulating fresh air so drivers wouldn't suffocate during the 15-minute journey through the mountain. 25 separate tunnels, each one a feat of engineering that would make headlines on its own, all completed as part of a single highway project. And it wasn't just water and earthquakes the engineers had to worry about. The Yaxi Expressway sits directly on top of multiple active fault lines. Not near them, on top of them. The same tectonic forces that created these mountains are still moving, still grinding, still building pressure beneath the surface. In 2008, a magnitude 7.9 earthquake devastated Sichuan province, killing nearly 70,000 people and destroying infrastructure for hundreds of miles. Engineers designing the Yaxi Expressway knew their highway would face the same forces. Every bridge, every tunnel, every mile of roadway had to survive magnitude 8 earthquakes. Traditional highway design would crumble the first time the ground moved. For engineers, the bigger problem wasn't building strong structures. It was building structures that could move. Earthquakes generate lateral forces that snap rigid bridges like twigs. The ground doesn't just shake up and down, it shifts sideways, sometimes several feet in seconds. Bridges that can't flex with that motion collapse onto the valleys below. Tunnel linings crack when mountains shift around them, turning safe passages into death traps. The Yaxi Expressway was being built on ground that would literally move beneath it, and there was no way to stop the earthquakes from coming. Testing revealed that standard construction methods would fail within years, maybe months, of the first major quake. What these engineers created changed everything. Every bridge on the Yaxi Expressway sits on seismic isolation bearings that let the deck move 3 feet in any direction during an earthquake. 3 feet. The bridge doesn't fight the ground, it rides with it, sliding on bearings designed to absorb and dissipate the violent energy. Flexible joints connect every segment of roadway, allowing the expressway to bend and flex like a snake instead of snapping like a stick. Inside the tunnels, reinforced linings incorporate flexible materials that can withstand the mountain literally shifting around them. Engineers didn't just test these systems. They tested them beyond worst-case scenarios, simulating earthquakes more powerful than anything recorded in the region. The highway was designed to survive the big one that hasn't happened yet. But there was one challenge that couldn't be solved with better materials or smarter design. Building at sea level is hard enough. Now imagine doing it at 13,000 feet above sea level, where the air is so thin that every breath feels like you're suffocating. The Yaxi Expressway doesn't just climb into the mountains, it climbs above the clouds. The Jiagenba Tunnel sits at 10,627 feet elevation, making it one of the highest tunnel construction sites on Earth. Workers showed up for their shifts and immediately felt their lungs burning, their heads pounding, their bodies screaming for oxygen that wasn't there. At the highest sections of the expressway, the atmosphere contains 40% less oxygen than at sea level. 40%. You're basically working on top of a mountain while trying to build a highway. This is where everything almost collapsed. Concrete doesn't cure properly in thin air. The chemical reactions that turn wet concrete into solid roadway depend on specific atmospheric conditions, and those conditions don't exist at extreme altitude. Batches mixed perfectly at lower elevations turned into weak, crumbling material when poured at 13,000 feet. Workers started passing out on the job, their bodies unable to function without enough oxygen. Some collapsed and had to be evacuated to lower elevations for medical treatment. Equipment designed for sea level lost power in the thin atmosphere, diesel engines gasping for air just like the workers. Machinery overheated and broke down at rates that destroyed construction schedules. Materials behaved unpredictably, expanding and contracting differently than engineers expected. The entire project ground to a halt as crews realized they couldn't build a highway using methods that only worked at normal elevations. Then came the solutions that made the impossible possible. Engineers developed oxygen-enriched concrete mixes, specifically formulated to cure properly at extreme altitude. The chemical composition was adjusted to account for lower atmospheric pressure and reduced oxygen, creating material that hardened into roadway just as strong as concrete poured at sea level. Portable oxygen stations appeared at every work site, letting workers breathe supplemental oxygen during their shifts. It wasn't just a comfort measure, it was a survival requirement. Equipment got retrofitted with turbochargers and forced air systems that maintained engine power even in thin atmosphere. Construction vehicles that would normally struggle at altitude operated at full capacity, keeping the project moving forward. 7,000 workers rotated through shifts, acclimatizing to the elevation while building one of the most ambitious highways ever conceived. 5 years. That's how long it took to complete what everyone said couldn't be done.